Welcome back to geometry. I'm a little bit excited, a little bit, because we actually get to talk about something that's a little bit more interesting and something that if you want to have a conversation about and have a course in, we could do an independent study, such as your senior seminar for those of you that are math majors or even the education majors that might want to uh, could look into mathematics and we could look into topology. So let's take a wee detour into topology. The first thing that we need to do before we make it into our detour is we would like to fill in that blank from the last video. And we're going to say that for the three-dimensional objects that we were looking at, v minus e plus f is equal to 2. Excellent. So continuing on with polyhedra, what we can do is we can add edges. So let's say we take this cube and then on this face we add an edge. So this face that was a square becomes 2 triangles. So in the first case, the number of vertices was 1, 2, 3, 4, 5, 6, 7, 8. The number of faces is 6 because that's a cube. And the number of edges, there's 4 on the top square, 4 on the bottom square, and then the 4 verticals, so 12 edges. But what we've done is we've kept the same number of vertices. We still have 8 vertices. The number of faces has increased because we took one of them and split it into 2. So now there's 7 faces. And let's see here, edges, well, we added 1 edge. So E is equal to 13. Now notice that in both cases, V minus E plus F is equal to 8 minus 6 V minus E. 8 minus 12, that's a bit different there. 8 minus 12 would be a -4 plus 6 is equal to a positive 2. Excellent, that's what we expected. But how does adding this edge change things? Well, it doesn't. V minus E plus F, V is 8 minus 13 is a -5. -5 plus 7 is still equal to 2. Doesn't matter that we changed it. We could add another edge if we wanted to. Add an edge here. What does that do? That increases our edge count by 1, adds 1 to the face. So those cancel each other out, and we still have 2. All right, so this stays exactly the same. But let's go ahead and extend this just a little bit. So in our example so far, we had faces, which were polygons. But if we allow those faces to have form to them, to round and to bubble, so that way rather than calling them faces on a cube, we could take round objects and put squares on top of a round object. Okay, so if we do that, we can take shapes that we're familiar with and put a grid on them, essentially. Put a graph, you might say, on them. So Euler's formula, given on the previous page, stays the same no matter what we're looking at for anything that's topologically equivalent to a sphere. But what does it mean to be topologically equivalent? Well, two surfaces are topologically equivalent if they can be morphed into the same thing. So topologically equivalent to a sphere means that they can be morphed into a sphere by shrinking, stretching, and molding, so moving it about. But what you can't do is you can't rip, tear, puncture or glue. So if you had a ball of Play-Doh, right? Anything that you can make that ball of Play-Doh into without ripping that Play-Doh, without poking your finger through the Play-Doh, and then you can't really glue Play-Doh together, but if you were to put two pieces together, they would stick. So you don't want to do that. So anything that you could just mold it into, okay, that would be all topologically equivalent to a sphere. So for example, if I had a football that was made out of clay, I could just squish it and it would be a sphere. A basketball is a sphere. A softball is a sphere. And a soup can, well, if it were made out of clay, I could push it into a sphere. So what we want to do is we want to notice that these excellently drawn sports balls are, right, they all have lines on them already from where they're sewn together. So if we think of those as our edges and then add appropriate vertices, because you can't just have an edge, then we can find vertices, edges, and faces. So if we wanted to, if we take a football, I believe that those are split into there are 4 pieces that are sewn together. So those 4 pieces give us our 4 faces. So faces is equal to 4. And then if we were to say that we have a vertex here and a vertex kind of hidden back there, kind of back there, then we would have this line. So well, that would give us 2 vertices. And then as far as the edges go, we would have the edge, we would have the 4 edges going from this vertex to that vertex. 1, 2, 3, 4 edges. V minus E plus F is equal to 2. All right, so let's take a look at a basketball. Well, for a basketball, we've got one line that kind of goes all the way around and another line that goes all the way around, and then we've got 2 more additional that go all the way around. But we've got them intersecting in several places as well. So if we realize that it looks the same on both sides, right, then we could say, all right, well, there's going to be 3 more intersections on the other side as well. So we would have, oops. So we would have that one and this one, and then this guy would come over here, and this guy would be somewhere over there. So that can get kind of messy looking. That's why I didn't draw it initially. So if you're like, oh man, what's going on? Just go ahead and rewind a little bit, get rid of those red lines, and don't bother copying them. I think I might actually delete them for now as well. So you don't have to worry about that. So if we were to count the number of vertices, there are 3 on this side and then the same 3 on the other side because it looks the same on the other side. So there are 6 vertices. And let's see here, for the edges, there are quite a few here. So there's 1, 2, 3, 4, 5, 6, 7, 8 edges, and then there's also edges between here. So 8, 9, 10, and then the same thing on the other side would give us 11 and 12. 12 edges, and then for the faces, there's a face here, face here, face here, face here. So that's 1, 2, 3, 4 faces, and then again 5, 6, 7, 8 faces. So V minus E plus F, 6 minus 12 is a negative 6, plus 8 gives us 2. Every time, every time. Now for a softball is just two pieces of leather wrapped around each other. Okay, but we need an edge in there somewhere. So there's only one seam joining the two pieces of leather. So if we just put one vertex on there, then we would have a beginning and an end of our edge. So there's only one vertex, there's only one edge, and then it's just the two pieces of fabric that are sewed together. V minus E, 1 minus 1 is 0, plus F, the number of faces, is 2. Same thing. Soup can, this one gets a little bit interesting, right? Because we can see an edge here, and we can see an edge there, but they're not actually connected. So we got to add a line, add an edge, so that gives us 2 vertices. Add them out here and then move them. 2 vertices. Close enough. Excellent. So there are 2 vertices. For the edges, there's the edge connecting the 2 vertices, and then the loop at the top of the can, loop at the bottom of the can to give 3 edges. And then the faces are the top, the bottom, and then the one face that goes all the way around. So V minus E is a -1 plus 3 is 2. Every time. For anything that's equivalent to a sphere. Anything that can be squished into a sphere. So for each example above, this is called the Euler characteristic. That number is called the Euler characteristic. Euler characteristic. Excellent. So they are all the same, Euler characteristic of 2. However, there certainly are surfaces that have an Euler characteristic that is not 2. So consider yourselves hungry for breakfast. You want a donut. So draw a donut. Big, ginormous, delicious looking donut. All right. So with this is just the surface. It doesn't have any vertices or edges on it. If I were to add a vertex right there, let's say, I could give an edge that goes around the inner tube, around the donut. All right, cool. And then if I wanted to, I would want to add another one that goes around the top here. Excellent. So like that. If I do that, what I have is I actually have one vertex. I have 1, 2 edges. And then there's only one face here. Notice that if I were an ant and I couldn't cross over the red line, I could actually get anywhere. If I were right here, I could go down underneath and end up on this other side. And then I could just wander around, go down and come back up, and I can go anywhere that I want. So there's only one face here. So here, V minus E plus F is actually equal to 1 minus 2 plus 1, which is 0, not 2, right? That's not 2. So essentially what it works out to be is it's a question of how many holes does the surface have, right? This is a donut has a hole. Coffee mug, right? This hole doesn't go all the way through, but the handle to a coffee mug, that goes through. So coffee mug and donut, same thing, for sure. So this is the idea of topology. What things can be shaped into other things? And yes, there are plenty of examples of molding a coffee mug into a donut. So coffee mug, two E's in coffee, into donut. Here we go. Here's a short video on it. Oh, look at that, look at that. Donut. And coffee mug. All right, so there you go. Same thing. If you have any questions about topology, you want to talk about it, take a look at it a little bit more, feel free to let me know. I'd love to have that conversation. Thank you for joining me for now. We do have one more video for this section on polyhedra, so I'll see you guys for one more video on this subject. See you in a little bit.